Welcome to AP Chemistry at Hananiga High School. I'm Brian Brown, and today I'm going to take a look at if you're having trouble with thermochemistry. Sometimes you look at a problem, you're just not sure what to do or where to go, because a lot of times if you can find the right starting point, it's going to make doing the solution of the problem a lot easier. So I want to go through and break down some of the different problems and things to watch out for if you're still struggling with this. Now you'll notice that I'm not taking all to final calculations because a number of these are types of questions that may be on my review. So I want you to be able to do the calculations. But I want to point out some of the pitfalls and some of the things that you need to be aware of. First off, if we break the chapter down, these are really some of the different things that we've looked at in the chapter. So the questions on the test related to mathematics are going to be related to these different ideas. Now, the first two here, kinetic energy and work, I'm not actually going to go through and do any calculations because really it's a plug and chug, but you need to be aware of a few things. First off, kinetic energy equation is 1/2 mv squared. So that's the calculation that you're going to be doing. Now, it may say calculate the kinetic energy of a moving particle, or it may just talk about finding the energy of a moving particle. Remember, kinetic is dealing with moving. So if you see anything related to motion of a moving particle, then you're doing 1/2 mv squared. The biggest thing to watch out for in this is typically they're going to ask you to calculate the energy in joules. And what that really means, since a joule is a kilogram meters squared per second squared, is you need to realize that this is locking us into very specific units because joule is SI, and SI, kilogram would be the SI mass, meter would be the SI length, and second would be the SI time. So the biggest thing to watch out for in this calculation is am I in the right mass? Am I in the right distance unit? And am I in the right time unit? That's the biggest thing to watch out for there. Same thing is true really with the work equation. Work equals force times distance. So the equation you're actually using here is the work is, oops, let me start that over. Work, W, is going to equal force times distance. The force you're applying over the distance you are fighting against it. That would be your work, and work is a form of energy. Just like kinetic energy is energy, so is work energy. So in this particular case, the thing to watch out for here is the same thing. The SI unit of force is the Newton. So if you see newtons, once again, that's an SI unit. That's going to lock us into masses in kilograms. It's going to lock us into lengths in meters and time in seconds. Those are the two biggest things to watch out for with those equations. So they're often really getting proper units before you do the calculation type problems. Now, the next one is internal energy, and I just want to take a real quick look at this one as well. Now, internal energy, so what is the change in internal energy? That's going to equal Q plus W. Now, Q is our heat portion of this type of energy. And when you're looking at Qs, remember it makes a difference whether you're endothermic or exothermic, because the trick to this question is really getting the right sign convention for your Q and W, because they're going to tell you whether positive or negative. They're going to say it's an endothermic reaction and the heat energy was 12 kilojoules. So it's endothermic, 12 kilojoules. Well, what you need to understand is endothermic energy in, that's positive. So in my equation, I'm going to plug in a positive 12 kilojoules. Now, sometimes the words are used besides endo or exo, that can be a clue. Because it may say something like 12 kilojoules of heat energy is added to the system. Well, it's not saying endothermic, but you're talking about adding it to the system, so it's going to be a positive value. If it says release from the system, it's going to be a negative value. So when they're telling you something related to Q, it's all about finding whether the Q is positive or negative before you plug it in. Same thing would be true with work. They're not really going to tell you whether the work is positive or negative. You're going to have to decide it. Remember, there's two situations. You either can do work on a system by the surroundings, in which case work is being done on the system by the surroundings. That's the system gaining energy. That's going to be a positive W situation. But if it describes the system as doing work on the surroundings, that means the system is spending energy. It's going to be a negative work value. So really, when you do internal energy problems, it's all about whether you're positive or negative in Q and W. And that's really it. The only other thing you watch out for is if they give you one unit in joules and the other in kilojoules, change to a common unit. Now, the rest of this is really the meat of the chapter with the different types of calculations we've done. Energy stoichiometry is one type of problem. Calorimetry in two different forms, Hess's law, and then calculating delta H using formation enthalpies. Those are all the other situations that we look at. Well, energy stoichiometry, what's happening there? Well, in energy stoichiometry, you're going to be given a chemical reaction 100% of the time. So you're going to have some chemical reaction, and they're going to be telling you what the enthalpy of that reaction is. Now, they might not say delta H equals whatever and write it next to the reaction. It may say in the words, for the following reaction, the heat released when the reaction occurs is 12 kilojoules of energy. Well, it says heat released, so that would mean it's a negative 12 kilojoule situation when you write it as a delta H. But they're describing the energy of that reaction actually occurring. Now, if that's the case, they're giving us really a thermochemical equation, a balanced chemical reactions with states. You'll notice they always have states in these. And they're telling us the energy that is either gained or released when that reaction happens. If you ever see that, and they're telling you the masses or the moles of any of the substances in the reaction and asking you to find energy, or if they're giving you energy and asking you to find how much in terms of mass or moles it would take to give off that much energy in one of the substances, then you're going to be doing energy stoichiometry. Remember, stoichiometry is when you're going from information about one substance to information about another. In essence, that's what we're doing in this question. They're telling us a balanced thermochemical equation. They're giving us information in the form of a mass or a mole amount of one of the substances, or they're giving us information in the terms of how much energy really was released or really was absorbed when the reaction happens. They're either going to tell us an amount of substance or an amount of energy, and we're going to have to work back the other way to solve it. We'll take a look at one of those in a second. Now, next would be calorimetry. Calorimetry comes in one of two forms. Now, they're both MC delta T, but really they're two different situations, and you need to recognize the difference because it's going to cause a difference in sign. Now, first off, if you are warming up or cooling off a substance, that's all you're doing is warming up or cooling off an object. You've warmed up water from 25 to 50 degrees Celsius. You've cooled off a block of aluminum from 12.5 degrees Celsius to 4.2 degrees Celsius, whatever. When you are warming up or cooling off a substance, you are going to be using Q equals MC delta T. It's a straightforward calculation involving Q, MC, and delta T. Now remember, Q would be the heat involved in the reaction, and it's going to end up either positive or negative, depending whether it's endo or exo from that object's point of view. Was it gaining or losing energy? Was it absorbing or releasing energy? The M would be the mass of the object. The C would be the specific heat of the object. And the delta T would be the temperature change of the object. Remember, delta T is final temperature minus initial temperature every single time. So delta anything is always final minus initial. So if you're warming up an object or cooling off an object, you just plug it right into that equation and solve for the variable they're asking for. Now, the one you see a little bit more often and involves a little bit more complexity is the other type of calorimetry. And if it ever says anything about coffee cup calorimeter, then you're going to be using this equation because what you've got in a coffee cup calorimeter is water with some chemicals or some object in the water. And you need to understand we're measuring what's happening to the chemicals or the object by looking at what's happening to the water, which would be the surroundings. And that's why it's a negative MC delta T situation. The Q of the reaction that we're looking at, whether it's an object warming up or cooling off in that water, or more likely some sort of chemical or physical reaction occurring in that water, when that chemical or that substance undergoes this change in energy, then it's going to affect the water. And we're not measuring the object. What we're measuring is the temperature change of the water. So we're looking at the mass, the specific heat, and the delta T of the solution. But from the reaction's point of view, it's going to be opposite in sign. What the water gains is what the chemicals lost. What the water loses is what the chemicals gain. Magnitude is the same, the difference is the sign. So it's the same energy, but going in a different direction. So we need to remember if we have a coffee cup calorimeter, those keywords, or if it's talking about a solution situation, it's negative MC delta T. And that sign can be very important in getting a problem right or wrong. So those are calorimetry problems. Now, one big distinction here between when we're talking about calorimetry, our Q things, and something like energy stoichiometry, you need to realize in delta H's, when we're looking at enthalpy changes, notice our unit here was kilojoules. But because specific heat, as we use it in a problem, is always going to be units of joules over gram, either degrees Celsius or Kelvin, because it's technically a change in temperature, and the change in degrees Celsius will be the same as the change in Kelvin, we're locked into joules. So when we're doing Q calculations, that means we're always going to be dealing with joules. When we're dealing with delta H enthalpy change reactions, you're going to be dealing with kilojoules. And when you're going back and forth from one to the other, that's a really important distinction to catch. So be careful with sign and also be careful with units, especially if you're calculating a Q using energy stoichiometry where you're going to get an answer in kilojoules. Now, next type of problem would be a Hess's law problem. And that one's a dead giveaway. If you see they're asking for the delta H of a reaction and they give you other reactions, you're going to be doing Hess's law. We'll see that in a second. And then finally, when you're calculating formation enthalpy or calculating formation, or when you're calculating delta H's of a reaction and they're giving you a reaction and that's it, then that means you're going to be using formation enthalpies because you don't have enough information to do anything else. Now, on a test question, it's probably going to be a dead giveaway because along with the reaction that they're asking you to find the enthalpy change of, they're going to have to give you formation enthalpies. In a homework problem, you just look it up in Appendix C. But in a test situation, you have to be given formation enthalpies. So 6 and 7, when you know what to look for, they really stand out. So let's look at some of these and try and evaluate which situation do we have. Okay, first one, the specific heat of lead is 0.13 joules over gram Kelvin. Remember that little dash just means joules over gram and Kelvin, it's not subtract. How many joules of heat would be required to raise the temperature of 15 grams of lead from 22 to 33 degrees Celsius? Right away, I see delta T. So I know this is going to be one of those Q equals MC delta T situations. The only real question is this a coffee cup calorimeter solution type situation, or is this just straight Q equals MC delta T because I'm warming up or cooling off an object? So look at the situation. Does it ever say coffee cup calorimeter? No. Does it ever talk about a solution? No. So that means when we go to do this one, we're just going to be doing a plain Q equals MC delta T. Now remember, we have a constant and 3 variables here. And you can be asked to find any of these things. In this case, they're asking how many joules of heat. So what we're actually calculating is a Q. So we should have the mass, we should have the specific heat, and we should have enough information to find our delta T. So this is an example of a plain old calorimetry problem. You're just warming up or cooling off an object. Plain old Q equals MC delta T. Okay, next problem. From the following enthalpies of reaction, they give us 3 reactions and their enthalpies. Calculate, and these should all say delta H's, calculate delta H for the reaction of ethylene with F2. So they're now asking us to find the delta H of this 4th equation. This is a dead giveaway. It's a Hess's law problem. One of the easiest ones to stand out because the fact that they're asking about the delta H of a reaction and they're giving us 3 reactions with enthalpies that we can use to calculate that one. And remember, it's manipulate these equations so that they add up to the 4th equation, using the 4th equation as a clue as to what should be where, and how you change the equation, you have to change the enthalpy in the reaction. And then once you get it to add up to the 4th, then that means their enthalpy should add up. So remember, you have to flip, then you multiply by -1 in the enthalpy because you're going from endo to exo or vice versa. If you have to double, then you double the energy because enthalpy is a type of property that changes with amounts. If you remember, that's called an extensive property. And if we had to cut in 1/2, then you're going to cut the energy in 1/2. So this is just a Hess's law type problem. Now the next one, consider the following reactions. So they give us a reaction and they're giving us an enthalpy change. That's driving me nuts. So that's a delta H right there. So pretend that says delta H. That didn't transfer when I cut and pasted in here. What is the amount of heat transferred when 5.6 grams of sodium reacts at constant pressure? So they're giving me a balanced thermochemical equation. They're giving me an amount of one substance and asking me to find out something else. Now, in this case, it's not a substance, it's energy, but this is energy stoichiometry. In order to do energy stoichiometry, I must have a balanced thermochemical equation. So if you see one, that's a pretty good guess that you're doing energy stoichiometry in some way, shape, or form. So really what's happening here is you've got sodium. So in this case, I've got 5.6 grams of sodium. And it's asking me how much energy is going to be transferred. Now, it doesn't really specify an amount. So in this particular case, since I see they give me an enthalpy, it's going to be kilojoules. So I'm going to go to kilojoules. So really all I have to do is get from grams of sodium to moles of sodium. And that's just a molar mass calculation you've done hundreds of times. And remember, this is moles of sodium. And now finally, if I know how many moles of sodium I've got, I could predict how many moles of chlorine. I could predict how many moles of sodium chloride. And I can also, in energy stoichiometry, predict how much energy. So from that balanced thermochemical equation, I know for every 2 moles of Na. So for every 2 moles of Na, I have negative 821.8 kilojoules of energy. In other words, that much energy is being released. So at that point, make sure I plug in appropriate molar masses here, and I can calculate exactly how much energy. Now, the other type of energy stoichiometry is if they give me how much energy. So they give me a balanced thermochemical equation, and they would say something like, how many grams of sodium would need to react to produce 17 kilojoules of energy? Now, it's talking about producing, so it's dead giveaway. We're dealing with an exothermic reaction here. But I'm starting with 17 kilojoules, and now I've got to work backwards. Kilojoules to moles. I can go from energy to moles using energy stoichiometry, and then moles to grams, and I'd be done. So energy stoichiometry is always going to be giving you a balanced thermochemical equation from which you can go from one thing to something else. Normally in regular stoichiometry, that would be masses and moles of one thing to masses and moles of another. In the case of this type of stoichiometry, energy stoichiometry, it's going between amounts of one substance and energy. Next question, determine the value of delta H naught in kilojoules for the following reaction. Now, they're not giving me much here. They're asking me to find delta H, kind of like we did up here in this Hess's law problem, but the difference is they're not giving me any other equations. So this is one where I'm doing formation enthalpies. If they're asking me to calculate a delta H, and that naught's kind of a dead giveaway too right there, because formation enthalpies, if you look, it's delta H sub F naught with that little circle there. That just means it's under standard conditions. I'm going to be using formation enthalpies. So in this case, since they didn't give me the numbers, then that means I would be looking them up in Appendix C. Now on the test, you can't look at Appendix C. You can't open your textbook. So you notice with this problem, they would give you the formation enthalpies for SO2 and the formation enthalpy for SO3. Those would have to be provided. They'd have to tell you the delta H of formation of those reactions. So if you're seeing formation enthalpies, then you're doing a formation enthalpy problem. Remember, it's the total on the product side. So look up SO3, multiply it by gas. Remember, states are important. So look up SO3 gas, find out what that says, and then double it. And then look up SO2. That's an arrow there making 2SO3. So look on the reactant side, 2SO2 plus O2. Well, you can't find O2. That's because it's zero. Elements in their elemental state don't take any energy to form. And then now you find your SO2 gas and you double that and then do the total on the products minus the total on reactants. You have your delta H. End of problem. Next one here. What is the molar heat of solution of lithium fluoride if 1.893 grams of lithium fluoride dissolves in 250 grams of water and the temperature changes from so on and so forth? Right there, I see that. I know it's Q equals MC delta T. The question is it plain old calorimetry or is it coffee cup calorimetry? Is it a negative MC delta T situation? Well, look at the problem. Molar heat of solution. That's talking about how much energy is involved when lithium fluoride dissolves. Well, it's dissolving in water to make a solution of water. And then it's talking about the mass of the substance and the mass of the water. This is a solution situation. So I know in this problem, the Q of the reaction, and that's what it's talking about, the molar heat of solution involved in this reaction, is going to equal negative MC delta T. And the big thing here, watch out for a few things. One, it's the mass of the solution. So don't use this mass, don't use that mass, use both of those two added together. So remember, it's dealing with the total mass of solution. C, we need the specific heat of the solution. Well, it's telling us the specific heat of water, and that's all it is. Usually this kind of problem also mentions something like, assume the specific heat of the solution is the specific heat of water. But you're going to see that number a lot. And then finally, delta T. Remember, that's final minus initial. So in this particular case, we're going to get a negative value. And that's then going to cancel with that negative value. So the Q of the reaction is going to be positive. So that means the reaction must be endothermic. Well, that makes sense. If the water was going down in energy, it was losing energy. So from the water or solution's point of view, that's exothermic. It's losing. So that must mean, where's that energy going? Well, it's going into the chemicals. It was gaining it. So the kinetic energy, or I should say the potential energy of the chemicals would be rising. So that's an endothermic situation. So yeah, it does end up getting positive endothermic, just like we think it would. So that's how you do this type of problem. Now, couple things about this type of problem. Now keep in mind, it says molar heat of solution. Well, what does molar heat mean? Well, that means energy per mole. Now, a lot of times they'll give you a clue in these type of problems because they'll give you like units. It'll say, what is the molar heat of solution? And then it'll say in parentheses, kilojoules per mole or joules per mole. In this case, it didn't specify, so we could do it either way. But you do need to understand it's a molar heat, so that's a per mole amount. So once we calculate Q to get energy per mole, we need to understand per mole of the reaction, which was lithium fluoride dissolving. So we need to change lithium fluoride into moles and divide. So that would be a coffee cup calorimeter type problem or a solution calorimetry. That's a negative MC delta T. Be careful of that sign. Next one, if the molar heat of the reaction of the following equation is negative 68 kilojoules per mole. Oh, so what they're telling me, and whenever I see this kind of thing, I really recommend you do this. Because they're telling me this. So what I've got is a thermochemical equation. Remember, with the thermochemical equation, I can do energy stoichiometry. It may or may not become important, but that's the first thing I see. I've got a thermochemical equation. Then it says when aqueous silver nitrate containing 1.032 grams of silver nitrate reacts with enough HCl to make the total mass of the solution 100 grams in a coffee cup calorimeter, the temperature increases from blank to blank. It's talking about temperature change. So once again, we're back to MC delta T. So we know we've got a Q equals MC delta T. The question is, what type of MC delta T? Is this in a coffee cup? Oh, right there it says that. Is this a solution? Yeah, both of those would indicate that I'm going to be doing negative MC delta T here. Now the problem is, it's asking me for this, the initial temperature. Well, that is related to that. So really what I want to do here is solve for delta T, and remember that delta T equals T final minus T initial. But do they give me a specific heat? Yes, they do. Because if I've got an unknown, I can only have one unknown. Do they give me the mass? Well, yeah, it says mass of the solution. So they're giving me the mass. And then finally, Q. Do they give me the heat? No, they don't. This is not a Q. That's a delta H. That's an enthalpy change. That's not the same thing as Q. So what I need to do in this problem is first find my Q. Well, that's an energy stoichiometry situation because you notice they give me the mass of the silver nitrate and I've got a thermochemical equation. If that mass is involved in the reaction and that's my balanced thermochemical equation, I can calculate how much energy. And that is going to end up giving me my Q. So the problem here is they do not give me Q. I have to find it using energy stoichiometry. So this is actually an MC delta T, a calorimetry problem with an energy stoichiometry problem involved in it. That's why I put it's tricky. You've got multiple things going on here. Watch units. Remember we talked about this early. Q is always in joules because our specific heat is always in joules. So when I calculate my energy and energy stoichiometry, I'm going to get kilojoules. Just like I always get kilojoules when I'm doing that. So be careful. You need to change to a common unit here in order to get to the problem to work. So that's what's going on in that one. There's a lot happening there. It's energy stoichiometry and it's a solution problem. Next one, hydrogen peroxide decomposes to water and oxygen at constant pressure by the following reaction. They give me a balanced chemical equation. They give me energy right away. I'm thinking, okay, I have a thermochemical equation. I can do energy stoichiometry. And sure enough, they give me an energy amount from which I can go from energy to the moles of either hydrogen peroxide or water or oxygen gas. And in this particular case, it's asking about the hydrogen peroxide. So yeah, I want to go to there. And then once I know moles of hydrogen peroxide, I can calculate the grams. So thermochemical equation, often a dead giveaway that it is energy stoichiometry. Now remember, if you're given multiple thermochemical equations, that's probably a Hess's law situation. Okay, a couple more here. I mentioned on the test, when you're doing a formation enthalpy problem, they have to actually give you the formation enthalpies. So sure enough, right there, I see a table of formation enthalpies. Dead giveaway, I'm going to be finding, and we already talked about this before, it's the same reaction. The total energy on this side, so right there. So I'm going to take that down there and times it by 2. And right there, SO2 gas, oh, that's that one. So I'm going to take that down there and I'm going to times it by 2. And then remember, you do products minus reactants once you have that. Now, why is that not up there? Because I need to know that one too. Well, elements in their elemental state. Oxygen is a gas. That's what elemental state means. What is it in this room right now? Well, it would be O2 gas. So that's going to be 0. Okay, next one. For which of the following reactions is the delta H not equal to the delta H naught of formation for the product? This is one that often throws students, and once you really realize what to look for, it's a pretty basic problem. Now, formation enthalpies. You're forming 1 mole of a compound from its elements in their elemental state. So I've got a requirement for the left of the arrow. I've got a requirement for the right of the arrow. One, I have to have elements in their elemental state on the left side. And 2, I have to be making 1 mole of product. Well, right away, if I look at the product side, every one of these is listed as 1 mole of a product. So I can't find my answer quick and easy way because they're all per 1 mole. But yes, if any one of those would have been other than 1 mole, I would know it would be the answer. So that must mean it's about the left side, elements in their elemental state. Well, if you take a look at the substances, carbon, that's a solid room temperature. Hydrogen, that's a gas. That's right. So that's elements in their elemental state. Can't be that one. Carbon solid, well, same reason above. Oxygen gas, that's a gas at room temperature. So that can't be it. Next one, magnesium. Well, yeah, magnesium is a solid at room temperature. Nitrogen's the other 80% of what I breathe in. That's not a liquid. That means that has to be the answer. This is not formed from elements in their elemental state. If that was a gas there, then yes, this would be a formation reaction that we're talking about, making 1 mole. So therefore, the delta H of the reaction would be the delta H of formation of the compound. So my answer has got to be C. And if you finish it off, yes, calcium is a solid at room temperature. Oxygen's a gas at room temperature. It's making 1 mole. So it can't be that one. That has to be a formation enthalpy. So okay, I want to finish up with just a few mention about units related to some of these things. Now, first off, keep in mind in energy stoichiometry, the type of unit we're going to be getting is kilojoules because the delta H's of the reaction that we're going to look at are going to be kilojoules per mole. But when we're dealing with Q's, what you're going to always be calculating will be joules. So remember, if you have to go back and forth between the two, like we're using energy stoichiometry to get a Q to plug into Q equals MC delta T to solve for M or C or delta T, fix your units. So be aware of that. The other thing related to units with this is pay attention to what kind of unit the question is asking for, because it may just ask what is the energy, in which case you're going to get joules or kilojoules, but sometimes they'll ask for molar heat, which is typically then going to ask for energy per mole. So they could ask for that, or they may ask for the energy per gram. So pay attention to what they want in units, because in each of these two situations, we're not done once we get to the energy. So however we ended up calculating the energy, which is typically going to be in a calorimetry situation, so we're going to end up with an energy. If we need kilojoules per mole or kilojoules per gram for the reaction that's taking place, remember you need to find energy and then find moles or grams and then divide. So in the case of a kilojoule per mole type situation, you'd need to convert this to kilojoules. And then in the problem, they're going to tell you the mass of the reacting substance, which we can convert to moles, and then plug that number of moles in here and divide. And then if they're asking for kilojoules per gram, Same thing. First, you got to change your joules to kilojoules and then find out the mass of the substance that was involved in the reaction and just put that down on the bottom. And that will give you kilojoules per gram. So pay attention to what type of unit they want in a number of these energy type problems. Now, the last thing I want to mention is really kind of number 8 here on my list, but it's unwritten. There's often confusion about the energy diagrams we look at. So let's say in an endothermic reaction. So let's say we had an endothermic reaction where A plus B was making C, and the delta H of the reaction was a positive 7 kilojoules. So that's what was given. And I ask you to write the energy diagram. So we're just going to draw a line, and that will be our reactants. So we're starting with our A plus B. And now, since it's endothermic, that means we're gaining energy. So we're going to go up to our products, which would be C. And the delta H for this reaction is going to be positive. In fact, we know, because it's given right here, it's going to equal positive 7 kilojoules. So that would be our energy diagram. Now, one of the confusions people have with this is when you're talking about the temperature involved here. So we know we've got A plus B. We know it's endothermic. So we hear endothermic is when heat energy goes in. Exothermic is when heat energy goes out. So students will think, well, heat energy is going in, so that must mean it's getting hotter. Well, you need to understand you're confusing types of energy here. We have potential energy, which is what this diagram is looking at here. So this is really a potential energy diagram, and this is increasing potential energy. So when we talk about A plus B going to C, and it absorbs energy to do that, it's absorbing heat energy, which is kinetic energy, and it's converting it to potential energy. So the system is not getting hotter when it's absorbing this heat. What's happening is the potential energy is changing of the system, not the kinetic energy. So I know we're talking about heat going in and heat going out, but when the heat energy goes in, it's being converted from kinetic energy to potential energy. So don't say just because it's endothermic, the system is getting hotter. If you're warming up water, yes, the system would be getting hotter. But when we're melting ice, the temperature isn't changing, but we're definitely putting heat in to melt the ice. Same thing is true with chemical reactions. When we're talking about chemical reactions, it's the potential energy of the system that is increasing. So heat comes in as kinetic, gets absorbed, and is converted to potential energy when the system gains energy. So just because you're adding heat and it's endothermic doesn't mean the system is getting hotter. In fact, in most situations, it really won't be. So be careful of that misconception related to what we talked about with the potential energy diagrams. And that ends the ideas that I wanted to get to with this chapter. Hopefully these help.